Hello everyone, my name is Zhiyuan Zhang. Today I will present our work on Soft-CCD algorithm for inverse kinematics of soft continuum manipulators. At promising research, the design and analysis of soft robots are increasing. However, there are still some challenging problems. Here we focus on inverse kinematics of soft continuum manipulators. SCMs are normally consist of flexible segments in series and driven by pneumatic or carbon actuators. According to the literature, SCM segments can be divided into three typical types. Their center arc can contract, extend, or keep constant, depending on the number of soft actuators arranged in parallel. There are two typical SCMs, the planar SCM and the 3D one. As for the single segment SCM, it is considered as a piecewise constant curvature arc. An intact SCM mathematical modeling has four sets of parameters: the actuator space, joint space, configuration space, and task space, which are connected by three mappings. At present, the kinematic problem of a single segment SCM has been well solved. As for the multiple segment SCM, the forward kinematics can also be solved by the classical DH transformation. However, as the segment increase, the inverse solutions will uprush. To quickly find a good inverse solution, here we propose the Soft-CCD algorithm, which is modified from CCD algorithm from a new point of view. Soft-CCD algorithm provides the following contribution to soft robotics. Firstly, it realizes iterations by directly updating the configuration space parameters of SCMs. Secondly, as the number of segments increase, the algorithm will play a more significant role with excellent computational efficiency. Thirdly, a random optimization method is designed to generate an appropriate length of each actuator in the physical limit range. Lastly, the CCD algorithm is generic on typical SCMs and is verified on multiple task scenarios. For the research contents, let me first show you what's CCD algorithm. CCD algorithm is a derivative-free optimization algorithm that can cyclically find a local minimum of an objective function. For IK of a planar hydro-redundant rigged manipulator, in one iteration, the joint angle alpha and the forward kinematics of the whole manipulator will be updated in turn to minimum the distance between the target position and the current endpoint of the manipulator. Since SCMs are not simply actuated by rotational or prismatic joints, and the shape of SCM is described by the center arc, bending angle, and torsion angle. Thus, CCD algorithm cannot be extrapolated to SCMs directly. To find the target position, Soft-CCD algorithm calculates the bending angle and selects a suitable length of the center arc for the planar SCM. The details of Soft-CCD algorithms are shown in these flow diagrams. By updating the configuration parameters and forward kinematics of each segment in turn, the algorithm can quickly find a good inverse solution. In addition, by adding the torsion angle into the diagram, the algorithm can be extended to 3D SCMs. However, for engineering applications, there are still several limitations. To solve these limitations, we designed several algorithm constraints. Limitation 1. The length of the actuator can be arbitrarily changed, but in practice, the elongated length of the actuator is limited and only changes within the physical range. We designed the random optimization method, which makes full use of the flexibility of SCMs. If the lengths Li1 and Li2 are within their physical limit range, the center arc Si will be calculated based on the geometric relationship. On the contrary, the value of SI will be selected randomly while meeting the constraints. Limitation 2. The abruptness in the bending angle theta is solved by a scaling factor to reduce the value of theta I. The actual value of theta I is divided by the number of rest segments. By doing so, this algorithm will obtain not only the final configuration of the SCM, but also a set of weighted intermediate configurations that lead to the appropriate solution. And our method can optimize the iteration speed and work at a weight factor to help keep the stability of the whole SCM. Thirdly, for kinematic singularity, when the target position in SCM are collinear, the bending angle theta I may result in a null value. In this case, it's possible to arbitrarily set a value in its physical limit range, because the movement of the next segment will help to avoid the singularity, benefiting from its flexible deformability. Then we test the Soft-CCD algorithm on a planar 5-segment SCM. Each segment contains 2 extensible soft actuators in parallel. At first, 4 single target positions are randomly selected in the Cartesian coordinates. When using the Soft-CCD without the constraint of center arc, the result is drawn as the left figure. It can be seen that the planar SCM found each target position in one iteration, and the error is 0. However, the lengths of some actuators are out of the physical limit range. When using the Soft-CCD with the constraint of center arc, the result is drawn at the right. The planar SCM can still find each target position in one iteration, and the error is also 0. As for the same target position, the length of each actuator is shown in Table 2. Compared to Table 1, the lengths of all the actuators are in the physical limit range. Thus, the random optimization method is verified. In addition, for the same target position in the first quadrant, we also tested the center arc contractile and constant planar SCMs respectively. The results show that the Soft-CCD algorithm is generic on different SCMs. The error of the contractile one is also 0. However, the error of the constant one is 1.6 mm. This is due to the flexibility of the center arc constant SCM is worse than the other 2 types, for lacking an axial degree of freedom. Then Soft-CCD algorithm was tested on SCMs with different segments, and we set the anchor base at the target position. After updating, a series of intermediate manipulator shapes are drawn. It shows that as the end effector moves cyclically to the anchor base, the final manipulator shape of the SCM is nearly a circle, and its trajectory tends to follow the golden spiral, which is common in the natural world. Next, we test the Soft-CCD algorithm on a 3D 5-segment SCM. Each segment contains 3 extensible soft actuators in parallel. Firstly, we set a single target position of the end effector. The SCM can find the target position in one iteration, and the error is 0. The average computing time is nearly 0.17 seconds. Then we set an arbitrary continuum target trajectories in the 3D space, which is discretized into 21 waypoints. The SCM can still find each target position in sequence without error. The average computing time is nearly 2 seconds. To demonstrate the fault tolerance ability, we tested the Soft-CCD algorithm when the third segment of the 3D SCM cannot work normally. The length of the 3 actuators that make up the third segment is fixed to 100 mm, which means the third segment always keeps the straight shape. The results show that the 3D SCM can still find each target position without error. Soft-CCD algorithm can also address multi-objective planning problems. To demonstrate that, we set two target trajectories in one task. Firstly, we said the SCM should pass through two similar pentagons. Secondly, we said the end of the third segment should pass through a common target position, before the whole SCM finding the target position of its end effector. Since the flexibility of the SCM decreases as the fixed segment increases, thus we set the default precision delta to 1 mm. The error is shown in the table. Finally, we tested the Soft-CCD algorithm on a real 3D couple-driven SCM, which consists of 3 segments. We set a circular continuous target trajectory, which is discretized into waypoints. For lacking the excess degree of freedom, the center arc constant SCM can only adjust its shape by the bending angle. Under this condition, the default precision delta is set to 3 mm. The tracking result is shown, and the maximum error is 4.14 mm, which is mainly caused by the assembly error and driving accuracy. To sum up, we proposed the Soft-CCD algorithm by calculating the configuration parameters of SCMs to address the inverse kinematic problems. Based on Soft-CCD algorithm, the numerical planar SCM quickly found all the random target positions in one iteration. Next, a numerical 3D 5-segment SCM showed it can track continuous trajectories, tolerate force, and complete multiple objective plannings accurately. Finally, the algorithm was tested on a real couple-driven SCM to track a circular trajectory. Thanks to the excellent flexibility of SCMs, our work provides a promising technique to solve the inverse kinematics of them. Thank you for your listening.